Okay, so let's take a second and kind of review what we had just started yesterday. We didn't quite get through this. We were looking at a polynomial. F of x equals x to the fourth minus 4x cubed. And let's see, we took both derivatives and we found both kinds of critical numbers. We found our first derivative critical numbers, which were 0 and 3, and our second derivative critical numbers were 0 and 2. And we were just in the process of kind of analyzing this guy, right? Now, remember that what we did, we first looked at this from the first derivative test perspective, right? And so to do that, remember we had to take our first derivative critical numbers, which are blue, and we picked some test points, and we looked at the sign of the derivative surrounding those test points, and that told us if those were, what kind of extremity they were, right? But now we're going to go back and we're going to revisit this. We're just in the process of looking at what this problem would have looked like if we had instead used the second derivative test, which we just kind of discovered yesterday, right? If we look at the concavity, and we're still sort of in the discovery process. I guess we're not quite there yet. What does the concavity tell us about, inflection points and stuff like that? But what does it tell us about the nature of the first derivative critical numbers? And we're just about to articulate what the second derivative test says. It's really cool. So we had these second derivative critical numbers, and we used test points surrounding them to see what the signs of the second derivative were over these intervals. And remind me real quick, what does a positive second derivative mean? Do you remember? Concave up, right? And we had we looked at some well, like this, here's a good one right here. Right, we looked at this just an example of this black function. And this would have been an interval right here where it's concave up, right? Concave up meaning that it's bowl-shaped up and that the tangent lines always sit below the function, right? Here are some intervals where the second derivative would be negative, which means that shape is concave down, tangent lines always sit on top of the curve, right?
Yeah.
Okay, so we did then identify these as transitions. These second derivative critical numbers were both transitional points for the second derivative, meaning it changed signs. So what does that make them? What do we call those?
Inflection.
Yeah, those are the inflection points, right? And if we go back to our picture, inflection points we said would be like right there. We identified them. Right there, you guys told me to stop. Remember? That's an inflection point. And that's an inflection point.
It's where it changes from one to the other.
Yeah, changes concavity from up to down or vice versa. Okay, those are inflection points. And we'll explore. I think I gave you an example. Just it wasn't a real big deal, and it probably didn't make a ton of sense. But maybe get an idea that the inflection point is also meaningful. Like in economics, I think I mentioned how point of diminishing returns a lot of times is identified by the inflection point. And we'll get into. I'm really anxious to get into those problems. We got a whole. We're going to kind of close up the year with another applied, sort of like related rates, only not harder, but just bigger and cooler. Does more stuff. So it's like related rates on steroids.
That sounds harder.
That sounds a lot harder.
I know it sounds okay. Bad choice of words. What's that? No, just going to cover this stuff. Yeah. Okay, so anyway, let's take a look. So we identified some inflection points, right? So we got these guys. This was an inflection point, and that's an inflection point. Here's what I really want to get at, though. We already identified this first derivative critical number because it was a place where we went from a decreasing first derivative, a negative first derivative, which is I guess I gave it away. What? You betcha. What does that tell you about the function if the first derivative is negative? Okay, we say it's decreasing, right? We always mean from left to right, so it's sloping down. So a decreasing function to an increasing function means what? What kind? If I'm going negative slope, yeah, it's gonna be a minimum, right?
Oh, yeah.
Okay, now that required though, notice that required that we test these 2 points, the signs of the first derivative surrounding that first derivative critical number. Now watch this. We don't even need those. Let's get rid of them. We can cut our work in half by instead just focusing on the sign of the second derivative coupled with the 0 of the first derivative. Think what this means now. We have a horizontal tangent line, and, right? And the concavity of the function there is what? What's that tell you? Isn't that cool? Think about that. Horizontal tangent line plus concave up means what? Means minimum, doesn't it? Right? See, that's the second derivative test. See how that works?
Yes.
Okay, so there's a way to remember that, and it's a little cheesy. If the first derivative is 0 and the second derivative is positive, that's a happy function, right? Okay, so it's thinking positive, that's a happy function. Now this other one, okay, so then the question was, what about this other first derivative critical number? Because it was a critical number of the first derivative and the second derivative, it was indeterminate. That means the fact that it's a first derivative critical number means it's a potential what? A potential extremum, right? That's where we know that all extrema have to occur at first derivative critical numbers. Not all of those are going to pan out, right? Some will be false alarms. All second derivative critical numbers second derivative critical numbers are potential what? Inflection points.
Yeah.
Once again, not all will pan out, but some will. And so it can't be both. It's one or the other. But at this point, we don't know which one because, well, we do now because we already checked. Right? Pretending we haven't checked, it would still be indeterminate. We just have to see which one is it. It's either one or the other. Well, because it is an inflection point, it can't be an extremum. Make sense?
Yes.
Okay?
Yes.
Is this stuff starting to kind of come together a little bit?
Yeah.
Okay, let's look at one more of these, and we'll rely on the second derivative test. Now, here's kind of the working rule for the second derivative test, too, by the way. The second derivative test is great when it works, when it's a good idea. When it's a bad idea, don't use it, right? Here's kind of the working rule for this table. There's a whole philosophy behind how to use this table. You want to work as far down the table as is convenient to do. It always requires less work to work on a lower row on the table. Okay, you get more bang for your buck to work in this row than you do in this row, right? But sometimes the second derivative is onerous and you don't want to do it. I mean, it can be a really bad derivative, in which case, if you don't need to. Now, if a question asks you to find out where the inflection points are, you don't have a choice. You got to take the second derivative, so you might as well use it. But if it doesn't, if you're only looking for extrema, which a lot of times you are, the second derivative is an option, right? And if it's an easy derivative to take, like it is here, I mean, if it's a polynomial, it's a no-brainer. Take the second derivative. It takes no time, and it makes your life a lot easier. But if the second derivative is going to be some enormous quotient rule, or, I mean, don't do it. Just use the first derivative rule then, or first derivative test, right? Okay, so let's look at another one.
Yeah, I think that's a good idea. I mean, I'm getting it. I'm getting it. Did you?
All right. How about?
Do a narwhal.
Okay.
Huh? Yeah. Dude, I love Anchorman. Oh god. It's it works every time.
How about that guy?
It just makes sense.
So let's find everything for this one. Oh, big little. And I want to do, I want to do one other thing today. I want to show you how you can add vertical asymptotes on one of these too, because that's also really cool. And then I think you're set up to work on this stuff for a while. Okay. So what do we do first here? Derivative. Okay, let's do the first derivative will be blue. Let's do that one. So what's the first derivative? 15x to the fourth.
Plus 15x squared.
Okay, there's the first derivative. Now we're going to have to, is that undefined anyplace? No, it's a polynomial, right? So we know it's not undefined. We're going to have to find the zeros. So let's go ahead and factor this thing, how about, right?
Okay.
What could I could take out what?
15x squared.
I could take, in fact, let's take out a negative 15x squared, right? 'Cause that way we want to make that first, right? So if we take out a negative 15x squared, what are we left with?
Minus 1.
Okay, good. So there's another way of saying that. That'll help us find the first derivative critical numbers. So that equals 0 when?
0, 1.
When x equals? Okay, this is giving us x equals 0. This is giving us x equals plus or minus 1, right? Okay, so we got our first derivative critical numbers. Let's go ahead and take the second derivative. Where do we want to pick up for the second derivative? Factored or unfactored?
Unfactored.
Unfactored, for sure. So we'll just go from there. And we get
60. Negative 6x cubed. Minus 30x.
Okay.
Plus.
And we can factor that. Let's see, if we factor that, we get, what do we take out? Good, negative 30x, leaving us with
Minus 1.
okay. And so this equals 0 when x equals what?
0.
0. Okay, or plus or minus, well actually plus or minus, so it'd be just 1 over the square root of 2. And we'll just leave the square root on the bottom, it's fine.
Yeah, we are rebels.
Okay? Right, so we got all our critical numbers. So let's build our table. Oh, you know what we never did in the last one?
What?
We never made our sketch.
Oh.
Oh, no.
Yeah, we never made our sketch. That's kind of the fun is being able to make a sketch.
Dirty right there.
So we got to make our sketch and then we'll.
I think you ought to just do it all.
Okay, so
I did too.
I hate to, so don't. I'm sorry to do that to you. Just we'll get back to the other one. Just that will be easy to catch up on the other one.
Okay,
So on this guy. So if you want to make a sketch, we've identified kind of the key elements. There's not much to this. Probably one thing to do is like if we know, for example, we have this minimum, maybe we want to know where it is. Right, so make an ordered pair out of that. So how do we find the y value?
Plug it in the
Plug it
original.
in, yeah. Plug it in the function. If I plug 3 in, let's see, what am I going to get? So I'm going to get,
No, just do.
what is it? So I can take out an x cubed, and then I'd be left with x minus 4, right? So what are we putting in? 3? 3? So x minus 4. So 3 minus 4 is negative 1, so that's going to be what, negative 27?
Yeah.
Is that right?
You know what I was thinking.
So there's our point, and then maybe we want to know where the point of inflection is. So if I plug 0 of these, if I plug 0 in, I get 0.
Wow, that's a straight line of zeros.
Okay, so then this is going to be slightly, so we're at 0, 0. Well, this is going to be not to scale, I guess. That doesn't matter though.
Whatever.
So we got something kind of like this, right? If it's going to be, we have concave up over here, so you know it's doing something like, and this is a point of inflection,
Going down.
so it's got to go,
Go back up.
right? It's got to be going down from left to right.
Mhm.
And then it's gotta change
And it's gotta go-
it's gotta
yeah.
change concavity at this point of inflection.
It's gonna go
So that's
the
where
other
it's
way.
gotta kinda make its transition to going down like that,
Yeah.
right?
Yeah,
Where do you kind of change this up, which one do you use, the first and second?
second.
Second derivative tells you concavity. Good, and then we get another, at 2, we get another shift, right? And so, boy, I gotta draw this a little more carefully.
Yeah, what is going on?
Didn't leave enough room.
I didn't really, did I? I'm not very artistic.
I think that's how it works. It's all good.
So it's concave down, then it switches about here to concave up, right? So it's gonna do something like that.
That's dirty.
Does that make sense?
I did that.
And that's the only way you can draw it. The specifics, I mean, we only anchored 2 points, so it's not like, did I get that right? Yeah, that's right.
Yeah.
If we wanted to make the sketch more accurate, we could add a couple more points, some actual points to run it through, but that's all we really need. We just wanna know kind of basically what's the
That
shape.
is indeed all we need.
Questions?
No.
Does that sketch make sense?
Yes, sir. Yeah.
These are, and these inflection points are useful, aren't they, right? There's no way. I don't think so. Yeah, I was hoping, but I don't think so. This is more important, trust me. This will be more valuable. Okay, so back to our,
I did that.
we started to jump around, but now we're going back to our current example. So we can make our table, right? We got all our critical numbers. So let's make this table. We got 0 plus minus 1, 0 plus minus 1 over the square root of 2. 1 over the square root of 2 is going to be about what? 1 over 1 point, so it's going to be about like 0.7071 something. Yeah.
Kelly just knows it. Kelly knows it's something. For sure.
Okay, so first derivative critical numbers were 0, -1, +1, right? And we had zeros of the first derivative. Second derivative critical numbers in between,
Right, so.
right?
That would be correct.
Okay, let's be as economical about this as we can. Do we need to do anything on the third row here?
No.
Don't, do we? Right? What are our test points gonna be for the second derivative? Whoops, I missed, there's one there too, isn't there? Sorry, whoops.
Okay, good. Thank you.
Whoa.
Okay, yeah, so we could,
Because it was x equals, yeah.
see, we can kill 2 birds with 1 stone here. We can use this first derivative critical number as our test point for the second derivative, right? Does that make sense? Okay, so let's evaluate, we've got a factored version. We want to use the factored version to test signs, makes it easy. So let's go ahead and tell me this. The sign of f double prime of -1, and here's what we're looking at, right? There's our factored version of the second derivative. What are the signs of the factors going to be? When x is -1, we're going to get
Positive.
positive times positive in this case, right?
Mhm.
So we get positive right there. What's that tell you that is then? That first derivative critical number is, yeah, it's happy. Good, so that's
Happy.
a horizontal derivative, concave up, right? What about at +1? Negative times positive is negative, so it's sad. Okay, all right,
Everyone
so,
understands happy and sad.
okay, so now what? Okay, these are our critical numbers, right? So the blue zeros come from here, because we want to know when is the first derivative undefined or equal to 0. We're finding the first derivative critical. Maybe I should have labeled those. These are the first derivative critical numbers.
Oh,
right?
so plus or minus 1, that's 3, or 2 right there, and then 0 is 2.
Yep.
Okay.
Does that make sense?
Yeah. I
So
get it.
these are, and let me label those. These right here, these guys. First derivative critical numbers, right?
Yeah.
First dirt crit hashtags.
That's right. And then down here, these guys are going to be where the second derivative is either, it's nowhere undefined, but where it equals 0. So,
And then 0, of course, is just 0, right?
well, 0 is a double critical number, so that's one we don't know. So that's what I want you to tell me now is, what? What do I do from here? It's this, see now, these were really handy because the first derivative critical numbers at -1 and +1 were not second derivative critical numbers. And so I used those values as my second derivative test points, right? Which simultaneously told me concavity, which is useful, and it told me what those extrema were, right? Okay, but I can't do that here because 0 is a critical number of both. So what do I have to do now?
Signs.
Need more test points, don't I?
Yeah.
So I'm gonna need a test where? What do you think?
Around
Give me
zero.
give me a value for a test point.
0.5.
Does that make sense? So in between here and here somewhere, right? Okay. Okay, so let's try like negative. We'll even play it safe, 0.25, just in case we weren't sure where that was. 1/4 or 0.25, right? So if we plug that in now, okay, here's the other question: which function do we plug it into?
Plug it into
So let's do the second derivative, and I'll show you why here in a second.
Watch.
The second derivative, we want to work as low as we can, because we've got the second derivative calculated. Always work as far down the table as you can. So in the second derivative, if I put in 1/4 here, -1/4, what do I get? Positive times negative, right?
Yeah.
1/4 squared is 1/16. 2 times 1/16, right, does that make sense?
1/8.
So we're gonna get, we said, positive times negative is negative. Okay, what about over here? It's gonna be positive, isn't it? Right? Only thing that changes is that part. Okay, so now, what does that tell us about this?
That one's side and that one's.
Okay, it tells us that this is
That is a point of inflection.
a point of inflection, isn't it? Right.
Yes, that's correct. I
Okay.
I got the 7.
That's all.
Okay, and so therefore, is it a relative extrema?
No.
It can't be. It can't be both. It's one or the other. It's an inflection point. Okay. So now that's all we need. That's all we need to sketch this thing, right? Doesn't seem like very much, but that's all we need. So you tell me. I want you guys to here take a second and sketch this. Try to just draw a rough sketch on your paper, and then you can walk me through it.
We need some points too?
Yep.
On the row,
I need to find this.
double times,
Mhm.
plus the far right, minus the far right. How do you guys do it? That's the second derivative?
It is right. Exactly. So all we did was we tested the sign of the second derivative at x equals -1 and positive. Okay, does that make sense?
Two, who needs some points?
Can you plug that into the?
You got, yeah, probably do. Yeah, you're right. You wanna do this right. You're saying,
3
Yeah,
plus.
minus 5. There you
Yeah.
Make-
-2.
All we do is just plug it in.
Oh,
Yeah.
yeah.
plug it into the original function, which
Plus
is
5.
that, if you wanna write it down.
-1. I
So
got
we
it.
go,
Okay.
do we grab this one constant?
Oh.
Oh, it's not even calculated, is it? It's -2, isn't it?
Yeah.
Plus.
when you go through, that's the problem with the inflection.
Oh.
Kendall, what are you doing? Come on.
Wait, so -3
That's what
minus,
It's awesome.
no, -3 plus 1. Wait,
Clayton's a stud, dude. Look
I
at
need,
that. Oh, but that is not correct.
Oh, we're doing negative. Yeah. I thought we were doing positive one, that's what was missing. So positive one is negative. So we negative one is negative one's here. Do I graph?
That's what I got right there.
So it goes,
That's fine.
when the plus is going down like that, and then the negative means
Okay,
it's
right
going
there.
back up.
Negative means
Whoa, whoa,
it's
whoa.
concave down.
So it's that's plus, that's negative,
No,
Positive one's
Negative.
here.
that's
Those are
negative.
the critical numbers.
and then plus again, no,
We'll see.
plus
I
again.
don't know.
So it's going.
Maybe I'm just not getting this 100%. We'll see.
That or I'm not getting it, I don't know.
So I guess I forgot to write, what are these guys here too? We already figured those out. Yeah, those are all.
Oh, yeah. Clutch, deploying.
So it should be zero.
Yeah, just start
Yep,
over.
all the second derivative zeros are inflection points. You see why? Because each of them is a changing signs. Okay.
What's your graph?
Looks like 2 parabolics with a x cubed.
No, they don't have to. I'm gonna show you some really quick, simple examples where they focus on.
With an x cubed in the middle.
Yeah. I'll just draw that.
That's what mine looks
So
like now.
What are these? Yeah, have you guys calculated these values already?
Yeah, I got 8,
8 for here?
yeah.
Whoa!
Oh, hey, oh, hey, oh, hey.
There.
I just have to.
Yeah, it's
This is
negative
negative
2.
two,
Yeah.
This is
Zero.
2.
Almost 5.
Okay,
Clutch.
Oh, I just have two?
I was wondering why I was so objective.
Kendall still suck on doing basic math. And substitution. He's having a little trouble on plugging checks. They're saying it just either.
That's
I
alright.
need to regraph this now because that's wrong.
Don't worry about it.
I know that's
So,
What is that your dad? I'm sorry.
I just kind of guessed. Kind of
Hashtag
embarrassing.
just did.
Very ashamed
Let's go.
of my graph.
It was.
So there are those 3 points, right? Here, I'll draw a point so I can color.
Okay.
Ooh, orange.
So it goes like this.
Oh, he was spaced out.
Okay, let's
And those
divide
are
this
orange?
up with our inflection points. So there's an inflection point, right? There's an inflection point.
Or I didn't line them up.
That kind of helps.
That's really smart. I should have thought
Oh, you drew it up with.
Oh, see, lining it up. Yeah, that's clever.
So
Oh, well.
I can't.
Whatever. I think it still grabs it right. Just not her day.
Okay.
It's because people like run across the river.
Have you seen her original back? Yeah. I'm sorry. I'm not.
Okay, so let's try this. What do we got here? What's this guy?
He's
Going-
Okay, good, yeah, there you go.
Valley,
So
the
that's,
valley.
so we're going something, I don't know if the, once again, this is just, oh, gee.
Oh.
There's a little cave in your concave up.
What's happening there?
It's gonna inflect.
He is-
What are we doing?
That's definitely.
Yeah,
And it's gonna go back. Yeah.
Whoa. That's kind of.
It switches again.
And then it switches again.
Okay.
And then it goes down.
Well, that's, you get the idea.
Yeah,
Yeah.
close enough.
I don't like this.
Okay.
Pictures.
Nope, I
You
don't
get it?
understand. What's that little cave in there doing?
I don't know, it's a little blip. It's a glitch, yeah.
Uh,
Okay, now, okay, I'm gonna show this to you. This is just too cool not to show you. Okay, let's go back to our original function here for a second. There's something else that you wanna take
oh,
advantage of.
God.
There's just so much that goes into this, but another great tool in curve sketching is symmetry. You always wanna try to take advantage of symmetry, because if you know the symmetry, a lot of times you could graph like half of a function and say, okay, because of the symmetry, the other half is a mirror image. So it makes it really easy, right?
Yeah.
Or the other half has rotational symmetry about the origin, right? So let's take this function, for example, and let's just explore, because this is really simple, and it's all review. You've done this before, whether or not you really emphasized it, or you may not have, but
That is handy.
okay, so and symmetry is a big deal. I mean, and just keep in mind that this is all, I mean, this is just the tip of the iceberg, really. I mean, we're looking at symmetry with functions right here, but symmetry doesn't have to be physical symmetry. It doesn't have to be, there are other kinds of symmetry too, like if you guys end up studying physics or something. In quantum mechanics, symmetry means completely different stuff. In quantum mechanics, symmetry might mean it might have to do with the spin of a particle or something. I mean, there's all these other symmetries you can take advantage of mathematically that it's just like this, right? So there's really two kinds of symmetry. I just want to show you. This is really helpful. We have even symmetry and odd symmetry. So even symmetry is this. Here's the test. F of negative x equals f of x. Okay? Odd symmetry says f of negative x equals negative f of x. What do I mean by that? What I mean is, here's the way you can always test this. If I substitute a negative x, every place there's an x in the function, when I simplify, if I get back what I started with, that's even symmetry. Give you an example. Here's an example of even symmetry. Okay? So watch what happens now. If we substitute a negative x, watch what happens. Okay, what's negative x to the fourth? The quantity negative x to the fourth. X to the fourth, right? The quantity negative x squared is just x squared, right?
Yep.
And so do you see here that f of minus x ends up being f of x, right?
Yeah.
So that's even symmetry. That's symmetry, if we were to graph that symmetry, that's symmetry about the y-axis, right? So this would be an example. That's not what this one looks like, but that's an example of even symmetry. So you graph the left half or the right half and fold it over the y-axis, right? Okay, what about odd symmetry? Odd symmetry would be something like the one we have right here, right? Ours is going to end up being odd symmetry. So if we take f of x equals negative 3x to the fifth plus 5x cubed, right? Now what happens? What happens if we plug in negative x? What's the quantity negative x to the fifth? Negative x to the fifth, right? So this ends up being positive 3 x to the fifth, right? Agreed? Yeah. And then this would be minus 5x cubed, right? And isn't that just equal to minus the quantity negative 3x to the fifth plus 5x cubed?
Yep.
Right? Well, that's f of x, right? So we just showed that f of minus x equals minus f of x, right? Make sense?
Mm-hmm.
Questions on that? Okay, so what kind of symmetry is that? Remember? Odd. Okay, it's odd symmetry, but what does it look like graphically? What's an example?
Over the x.
No. That's a kind of even symmetry also. Say it again. Oh no, it's not. That's I know what you're thinking of. That's symmetry if you have inverse relations.
Ridiculous.
It's different kind of symmetry. It's rotational symmetry about the origin. So for example, something like this. There's the left half, there's the right half. What this means is that the left half is just the right half rotated around the origin 180 degrees. Make sense?
Yes, it is.
So I just took this thing, put a tack in it, and I spun the whole thing half a turn, and it lined up. Okay? So with our graph, the sketch that we made for this, then we could have just sketched this half over here, right? And then said, okay, I know what this is going to be. It's odd symmetry, and so I'm just going to take this and do that to it. Right.
Oh.
And everything, notice even the points. The points are, see?
Ooh.
Stops the sign.
I noticed that. Yeah.
Okay. Now,
Actually, I did really.
can anybody tell me, and the examples that we used were intentional here. Can you tell me why it is? It doesn't really make sense in a way that you call this even symmetry and odd symmetry. Where's that come from?
Exponent.
Exponents, yeah. Because polynomials, it all comes back to polynomials. Polynomials are some of the most popular models that we use. And so we're just talking about the exponents. If all of the exponents in a polynomial are even, and what's the exponent that goes with 1 there?
0.
X to the 0, right? There's an invisible x to the 0. So a constant is consistent with even symmetry, right? If all the exponents are even, without even, if it's a polynomial, guaranteed, it's even symmetry. If all of the exponents are odd, it's odd symmetry. What if you have a mixture of both?
No.
It spoils it. It's neither then. There's no symmetry. Okay? Now, one last part of this, and I don't want to, we'll continue to work with this. Don't worry if you're thinking, oh my gosh, there's so much information. But with math, you just have to see it over and over again. It just kind of becomes part of you. But symmetry works like sign rules. So for example, if let's say I have a composition of functions. If I take some functions and I take a product of some functions, let's say we've got, for example, we end up with h of x equals g of x times f of x. If g of x has even symmetry and f of x has even symmetry, what do you suppose the symmetry of h of x is going to be? Even. If g of x has odd symmetry and f of x has odd symmetry, what do you suppose? Even.
Oh, it's
Even.
like the double.
Yeah. It's like sign rules. Okay. Does that make sense?
Yeah.
What if these have opposite symmetries?
Odd.
It's odd.
Flash.
Yeah. Same thing for a quotient. Okay. That make sense?
Mhm.
All right. Okay, so let's look at a couple really simple ones, but I want to make a point with this. Really simple. These will be very quick. What if we have something like f of x equals x cubed? So let's take the derivatives real quick. What's the first derivative? And second derivative?
Sharp Kindle.
Okay, so the critical numbers are all what?
The what?
Where are
Zero.
both the derivatives equal to 0?
Zero.
0, sure, 0. So this is a pretty simple table, right? We just get,
Yeah.
and so our only critical number is at 0, which is actually 0 everywhere, right? Pretty boring, it's all zeros. We want to work where on this one for our test points?
Just on one side.
But where on the table? Bottom, low as we can, right? So we'll use our test points will be like -1 and +1, let's say. What's the sign of the second derivative at -1? Negative, positive. So what is this? Inflection point, sure. And there's our point, and we get a sketch of this really easily, don't we? So this has to be right? We know this is, here's our dashed line, there's our point. If it's concave down over here, it just has to be like that, doesn't it? And that is the shape of a cubic function, right? Okay? Okay, so what's the point of that? Pretty easy. But now watch this. This is a little bit, now I want you to tell me what to do with this.
Dirty.
Same idea. Table looks identical, right?
0.
Bottom row, what do we get? Positive? Positive. Okay, let's analyze this. This one at first looks a little bizarre. So is it an inflection point? No, it's not. Now we don't need to do this, but for now, just so we can show that they're consistent, let's go ahead and revert back to the first derivative row. How do I get there?
Negative.
Okay, so that tells me we know what this is then, right? If that's our horizontal tangent line, if we're going decreasing to increasing, it's a minimum. Yeah, so we know it's gonna look like that, right? Okay, my claim is we don't need this stuff. We just need this. You know, now listen to this real carefully, and this will all come together. What does this really say about the function if there's only one critical number of both derivatives on the entire real line, right? So the concavity everywhere to the left of 0 is positive,
Yeah.
right?
Yeah.
The concavity everywhere to the right is positive, okay? Does it make sense that there could be positive concavity everywhere over there and everywhere over here, and somehow not have positive concavity at that point? I mean, think about the concept of concavity. Isn't concavity, if I say that a function is concave at a point, doesn't that really imply some kind of a relationship between that point and all its neighbors, right?
Uh-huh.
See my point? And so how could you somehow not have a point, does that make sense? How could you not have a point be concave up here and have it be concave up everywhere else around it, right? Because that's just one infinitely small point. If every other point around that is bending up, that doesn't compute, right? Doesn't make sense. You can't have, so this really, the point being that if you get a 0 of the second derivative, and it's a continuous function like this. I mean, if there's a break in the function, maybe we could see something like that, right? But there's not. This is a well-behaved polynomial. So if you have a continuous function and you get a 0 of the second derivative surrounded by the same sign on either side, that's really doesn't make sense. Really, you can think of that as being these pluses make that, they kind of, I don't know how you want to write that, but really it just kind of makes that a plus. It acts like a concave up then. It has to. It can't be anything else. In order for that to be concave down, it would depend on its neighbors also being concave down, right? Does that make sense?
Yeah.
Okay.
Yeah.
And so if we graph this thing, then, and you'll see when you look at the graph that it has to be that way, right? If this is our point, and we're concave up everywhere over here, and we're concave up everywhere over there, that's concave up too. It has to be. Right? And so that makes that a minimum. Okay? That make sense? So once again, you can just work only in the second derivative row. How we doing? That's probably about out, huh?
Yep.
Okay. That's probably good enough to get you going on this stuff for a while anyway.
No, when it's just